There we go. Okay, first thing with all these problems post 12 week is to just make sure that we read them to understand what's happening first. So we're starting in the system below, we have EAB. This is line A and line B. So this is a line to line voltage. On the formula sheet, it calls it line voltage, but this is a line voltage, not a phase voltage. The frequency is 60 Hertz. That's F. We'll see if we need that later. Now here we have a three-phase system. See these three wires coming in, and we have inside of this basically like a three-phase motor. So if we think of there's a resistor and an inductor, a resistor and an inductor, and a resistor and an inductor, and they're all these three phases, and we can think of this as like an elevator. An elevator needs all three phases of power. If you watch that three-phase power video on YouTube, you know, we said we could send a single-phase power to each floor, but the three-phase power is moving something. And let's say an elevator. It's easy to imagine, right? We need a motor to spin to move the elevator up and down. It provides 20 horsepower. This is P out, right? And that makes sense when we think of it's a motor and it's moving something. And so electrical power is flowing in these three phases, and then mechanical power is coming out, which is why I said horsepower, remember, is always mechanical. So now the first thing says determine the total output power in watts. So we just take that 20 HP, and we can do the railroad tracks, right? 746 watts over 1 horsepower. 746 times 20, and that gives me 14.92 kilowatts. We're still in real P power. This is still P out. All I've done right now is converted it, but you're going to need to convert it in order to use it in electricity, because everything that we're dealing in electricity is watts. All right, so calculate the total input power of the motor. So we have mechanical power coming out, electrical power going in, and how do we determine that is using the efficiency. And a part of why I do like this last part of the course is because it does give practical application to the stuff we've been talking about. So we have power flowing in to move our elevator up and down, but there's some, you know, loss in the line because of resistance, and there's some friction inside of the gears of the elevator. But we can solve for the P in by dividing P out divided by the efficiency. All right, so P out, 14.92 divided by 0.65, and we get 22.95 kilowatts. So now this is my total P power, because it's all three phases. There's only one elevator moving. This is only one P out moving. So this is all three phases combined together is making my P total. So I said P total, don't do those line problems. They're just there to invite, you know, scared midshipmen to use. But the smart midshipmen know to just do three-phase power, right? It's a really ugly looking 3. We'll redraw it. P total divided by 3. 7.65 kilowatts. That is my P of a single phase. And that's what we said this phi symbol is, single phase. We've taken the input power and we've divided it by 3. Any questions up until now? All right, so I'm going to clear all this out so we can scroll down, and yeah, we'll be able to solve the rest of it right here. Okay, so for this single phase, still single phase, reactive power, that's Q. So what we're looking for is Q of a single phase. There's a couple different ways to get this. We know the power factor that was given up above was 0.87. Probably the easiest way to find the Q is we can take this 0.87 P over S, right? And if I'm thinking of this single phase, I have that 7.65, right, of my single phase. and my S, and I can solve for my apparent power of a single phase. On the formula sheet, it doesn't show the magnitude, but it's not bolded and it doesn't have a vector over it, so it's not the complex S, it's the apparent power S, which is the magnitude of the complex power. And I can solve for S, 7.65 divided by 0.87. And I get 8.79, and this would be kVA because it's apparent power, right? So there's the single phase of S. And if I think about this as a power triangle, right? There's a power triangle here. Here's S is 8.97. Here's P, 7.56. So probably the easiest formula is to do Q is equal to the square root of 8.79 squared divided by 7.65 squared, right? That's just Pythagorean's theorem back to, you know, probably 9th grade, maybe earlier than that. 8.79 squared minus 7.65 squared gives me 4, I think when I carried all the decimals through, 4.34 kVAR. VAR is volts, amps, reactive, right? That's what the R is reactive, and it is inductive. And the reason I know that, one, is because pretty much all real motors in the whole world are inductive motors, almost all of them. We rarely have capacitive motors, but the other reason is because it says lagging right here, where it says lag. That word lag, we said lagging power factor means inductive, and I said that's something that you almost just have to memorize in this class. But there's other ways to think about it. The theta would have to be positive as well for an inductive. The other way that you could do this is if you wanted to take the cosine, inverse cosine of the power factor, that would give me a theta, right? And if I had the theta, then if I did complex power, I could do S of theta, or S magnitude with theta, and go from polar to rectangular, and it would give me the P plus JQ. That's another good way to do it, because then whenever the P comes out, I should see that it equals 7.65. And it's kind of like a sanity. If my P come out to 7.65, I must have done the math right. But either way, the Q in this part, this is the one part, part D, where you decide how you want to get to Q. You know, there's multiple ways to do it. As long as you stick to what's true about the power triangle, there's theta, there's Q. Right, as long as you stick to the power triangle, you can't go wrong. And now from here, it's the same power factor correction as we had before. There's like the same steps. We're on a single phase, and we said there's a small series circuit. And so what we're going to do is we're going to find the value of a single phase reactive power needed to correct it. And that probably should say FP to 1. Right? We had an inductive Q, so all we need now is Q is equal to 4.34 kVAR. This is why I said determine, even right here. I didn't say calculate, because there's nothing to calculate. All I need is to take what was an inductive, replace it with a capacitive. And those two Q's will cancel, so that what was a power triangle, the Q's equal 0, and P and S are equal to each other, right? That's power factor to unity. The Q's will sum to 0. So now we're going to find the reactance that we need. Well, if we need to do this, it says capacitive, so we're solving for X sub C. And the other thing is that it's of a single phase. And this is maybe the one thing that's different about this three-phase power, is to make sure that we're talking about the phase power, the power of a single phase, which is EAN. We were not given EAN, we were given EAB, right? So EAB is going to be divided by root 3 angle 30. But since I'm asked about, well, actually, let's put in the formula real quick, and then we'll discuss EAN. So EAN is of the single phase, so just make sure if you had EAB, you divide it by the root 3. The Q formula for this is the V squared over X, this X being X sub C. The reason why this one is the one we want to use is because on my single phase equivalent, if I'm trying to cancel, right, my inductive load, my Z load over here, well, whenever I place, and I'll put it in red, when I place this capacitor in parallel with it, right, it's this node and this node right here that I need to place it in parallel with. So if this was AN, I need to place it in parallel with the total load, which is also the same as the source, right? So big A, big N. If there was no line impedance, then it would be the same as the load side. But if you had a line impedance, we need to place it in parallel with big A, big N. So that's why this V here needs to be the EAN.
So I have a question about that.
So this EAN that we need was the EAB. And since it's just the magnitude, you know, if I wanted, I could just ignore the angle 30 because I'm just looking for the magnitude of the voltage. You know, so that's you don't have to take that shortcut if you don't want. I don't care if you know, do it with the angle. Just make sure that when you solve it, you just pull the magnitude out. So EAN comes out to 277 volts. So I put 277 volts, square that, and I solve for XC. So this Q was that 4.34. So X sub C 277 squared divided by, it's really 4,340, right? Because that was kVAR. So just when you plug it in your calculator, you don't just do 4.34, do the all the way. That's EAN over here. And I think that comes out to something like 17 squared divided by 40. Yeah, 17.7 ohms. That's ohms because it's a reactance. And now this is the last step. X sub C, the reactance, is dependent upon a frequency, right? And if we even think back to all the different frequencies like resonance and filters, different frequencies create different reactances. But what we need is the one of our particular circuit. So on our circuit, you know, the frequency we said 60 hertz, which is most common in America. Everything is pretty much on 60 hertz, all your wall outlets. So now we have 1 over 2 pi 60, and the X sub C was right there, the 17.7, and our final capacitance comes out to 150 microfarads. So this is a capacitor of a single phase. Okay, so this is not it's not like I'm going to take 3 capacitors and call it 450 microfarads. We're just going to call it of a single phase. That's all that I'm asking you to solve here, and that's usually what we're asking you to solve. Okay, so in here, what we had before was a source on one side. This wasn't really shown in the problem. It just said we have a line voltage. And then we said there's an inductive load over here that was that motor. And we modeled it by just putting it as a circle, right? We just had a circle that was our motor. And so then what ends up happening is whenever we plug this 150 in, we connect all 3 of those into a Y-fit configuration, right? And so this one right here connects to A, and right there inside it is neutral. Right here inside it is neutral. So there's a 150 capacitor, 150 microfarad capacitor connecting to each of them. And so this was B right here. This one is connected into B. Here's where A connects in, and then on this side is where C connects in. Right, and so we're going to plug in the capacitor in a 3-phase, but all we're asking you to solve for is of a single phase. And that's why this single phase equivalent is so powerful. Going from a 3-phase, what was complex, to this idea of a single phase makes it much easier to solve for just this one. That's also why whenever you're using the equation for Q, you're going to use V squared over X, and the V that you're going to do is just the individual VAN or EAN. Okay. I think that is enough